Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW Gulf. Students, I welcome you all to your Achievers Ultimate Recap session. That means, what are we going to do today? Today, we are going to revise the complete chapter of thermodynamics in this particular session. I hope so, students, you have done this chapter in detail, but now it's time to brush up your concepts. It's time to revise the complete chapter, just like in a flow. And we are going to do that with the help of your notes and with the help of your NCERT. If students, you have not made any notes till now, then it's best way to create short notes for the chapter thermodynamics so that whensoever you have your examination, you can quickly revise each and every topic. So how are we going to proceed in this particular class? First of all, students, let me tell you, we are going to understand each and every topic in detail. I will not be, deriving the formulas, but yes, I will be telling you the formulas because this is an ultimate recap session, right? So what you can do is you can create your formula charts, the formula sheets from this particular session. You can create your short notes from this particular session. That is going to help you in your examination. So that means when you don't have much time to, revise the complete chapter, you can go through the short notes and you can revise each and every concept in detail, right? So let's start with this particular class in our Achievers Ultimate Recap with the chapter thermodynamics. Now, the very first part, how are we going to proceed, ma'am? What are the today's target? Like, what is the sequence of completing the chapter? So, we very well know that over here, students, we are going to start with what are the thermodynamic terms, okay? So, again and again, I will be talking about what is the system, what is the surrounding. You shall be listening to these words when I will be explaining each and every concept to you. So, we are going to understand the very basic terms that are used in thermodynamics, such as system, surrounding, universe, then irreversible, reversible, boundaries. Okay, so these are certain terms that I shall be speaking again and again, and you shall be observing in the questions also, right? So, the very first segment that we are going to start with is going to be your thermodynamic terms. After the students, we shall be proceeding with the very first part in thermodynamics, that is about work and heat. So we shall be understanding in detail about the heat and work, right? Work done by the system, work done on the system. We shall be understanding the very basic parts of this. After the students, I will be introducing you to a term that is internal energy. What it is, ma'am? Internal energy. And after internal energy, we'll be proceeding with the very first important topic of the chapter thermodynamics, that is first law of thermodynamics. What are we going to do that? We are going to do first law of thermodynamics. Now see students, after first law of thermodynamics, we shall be, understanding about the applications with regard to the first law of thermodynamics that refers to as your thermochemistry, okay? So we shall be looking up to the applications part in which we are going to understand in depth about, certain terms such as we'll be understanding about enthalpy, entropy, second law of thermodynamics, okay? Hess law, enthalpy, second law of thermodynamics, entropy, then about Gibbs free energy, and at last about third law of thermodynamics. So basically, this is going to be the flow through which we are going to start with our today's session. Let's start with the very first part. First of all, ma'am, what do we refer to as the term thermodynamics? Thermo refers to as heat, right? Now, that means in this complete thermodynamics, in this complete branch, what are we going to do? We are going to understand about heat and its conversions, right? So what is thermodynamics? It is that branch of physical chemistry, or I would say the branch of science, which deals with the study of quantitative relationship between heat and other forms of energy and their conversions. So this is what is thermodynamics. As I've already told you what are we going to do, but let me tell you, we generally divide this chapter into three major parts. The very first we're going to understand about is first law of thermodynamics. The second one is going to be the applications related to the first law. That means the thermochemistry part. And the third segment that we are going to do will be about the second law of thermodynamics, followed by, entropy, change in entropy, and all of that stuff. So basically, we cover thermodynamics like this. But before understanding first law, before moving on to the applications part, we should at least know the various basic terms that are used in thermodynamics, right? So students, let us start from the very basic. The very first part, the very first term that you would be listening again and again in this chapter, in this session, that is system. What is a system? You will say, ma'am, system, I guess computer system. No, 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 not that system. System over here is something which is under our study. That I would say, if for example, if I am doing a certain reaction in a laboratory, so what is happening? I am performing something. So the part of universe that is under my study will be the system. Okay, ma'am. So what is surrounding? The part other than that in the universe which is left, other than the system, is surrounding. Are you getting my point? The thing, the portion that is under my observation is system, and the part other than that in the complete universe is surrounding. So what is system? System is basically something which is under observation. In other terms, you can also say that, or part of universe, or the part of universe which is under our study, is basically your system. Now what is the surrounding? For this you can even refer to over here as that system plus surrounding constitute your universe. When you will combine both of them, you are forming universe. So if you know what is system, what will be universe? What will be surrounding? Surrounding will be universe minus system. No. So the part other than system is basically surrounding, right? The part other than system is surrounding. Clear? So whensoever I will be referring to a term as system, you should know that this is the thing that is under our observation, right? Okay, now students, let's move on to the types of systems. See, basically there are three types of system that we shall be observing. The number first is open system, the number second is closed system, while number third is isolated system. So basically there are three types of system that we are going to study. The very first is open system. The name itself says open, something which is open. Now, if I have to draw this, I would say that, for example, I have this beaker with me and I have kept this on a flask. Oh, sorry, I've kept this on a heater. So basically what I'm doing over here is this beaker holds some of the liquid, let us consider. So this is an open system. Why this is an open system? Because there is an exchange of both energy and mass over here. Again speaking the thing, what is an open system? Where we can observe there is an exchange in mass and energy, both of the terms. That is what is open system. So you can say in an open system there is an exchange of energy and matter between the system and the surrounding. Now this is the beaker which is under observation, so this is a system. The part other than that which is not under our observation but it is present in universe is surrounding, right? So when I can say that energy and my matter both basically of this particular system is being exchanged with surrounding, that is an open system. How it can exchange, ma'am? See, for example, you have taken a liquid over here, you are heating it. So the vapors that are being created are the change of matter, exchange of matter from the system to the surrounding. Second part, you are heating it, so there is a change in temperature as well. That means there is an exchange of energy also taking place. So this is where we can say exchange of energy and matter both are taking place is your what? Is your open system, ma'am, right? So you can say the presence of reactants in open beaker is an example of open system, which I've already shown with the help of this diagram. Next part, here the boundary is imaginary surface enclosing the beaker and reactant. Now I'm introducing to you a new term, that is your boundary. Now what is a boundary, students? Boundary is something which separates both system and surrounding. What is boundary? Something. Now this something can be a line, can be a plane, Can be anything, okay? Something that separates both system and surrounding. That separates both system and surrounding. Yeah. So when both system and surrounding are being separated by a thin line or a plane, that is what is a boundary. Now there are various types of boundaries also. First of all, let me explain you what are types of system, then I will be letting you know what are types of boundary, right? Now come students, the next, that is closed system. Now closed system, the name itself says, ma'am, something is being closed from the top. Okay, if something is being closed from the top, that means what kind of exchange can be possible? There is no exchange of matter, but exchange of energy is possible between system and surrounding. Now from here, matter cannot exchange, but yes, energy can be exchanged. Energy can be exchanged. This is an example of closed system. The presence of reactant in a closed vessel made of conducting material, example copper or steel, is an example of a closed system. Now you very well know what is an open system, what is a closed system. Very simple term. Okay, so in open system I told you that there will be an exchange of energy and matter. In closed system I told you there won't be any exchange of matter, but yes, energy exchange will take place between system and surrounding. So now comes the third type of system, that is isolated system. In isolated system, what is going to happen? There will be no exchange, neither of matter nor of energy, right? So what is an isolated system? In isolated system, there is no exchange of energy or matter between the system and the surrounding. I'm just giving general example in the daily life if we can correlate with isolated system. So do you know about thermoflask? Yes, everybody, we do keep that in, winters. In that we keep just the hot water with ourselves so that we can drink whensoever we need to. So what happens in that sort of stuff? It is when it is closed from the top and it is a thermoflask. It will maintain the temperature also. That means there is no exchange of energy, no exchange of matter. But yes, if you'll open it from the top, yes, the exchange of energy and matter will take place. So thermoflask is an example of this part. In an isolated system, there is no exchange of energy or matter between the system and the surrounding. The presence of reactant in thermoflask or any other closed insulated vessel is an example of your isolated system. Now you know the types of system, students. Is it clear to each and every one of you? That's really great. Let's proceed with the next term that we are going to use is boundary and its type. So boundary, I've already told you. A thin line or something which separates both system and surrounding is what is boundary. But what are the types of boundary, students, if I'll talk about? See, one definition of boundary or one type of boundary, if I would say, the very first that we shall be observing is either real or imaginary boundary. Real or imaginary boundary. Now, what is a real and an imaginary boundary? The real boundary is something which you can clearly see. And imaginary is something which you need to imagine. That means real boundary can be seen in the case of closed system and imaginary boundary can be seen in the case of open system. Always remember, boundary is something which is separating both system and surroundings. So when I'm saying a closed system, it is closed from the top. You can clearly observe, right? So this is a real boundary. This you can clearly see with your naked eyes, right? But if I'll talk about imaginary ones, for example, if I have this beaker from open from the top and I have kept a liquid over here, right? So what is an imaginary boundary? This line is an imaginary boundary. This line is an imaginary boundary that separates the system and the surrounding. So this is basically seen in the case of open system, right? In the similar manner, students, if I have to explain you about the boundary and its types, I can say that rigid and flexible. The next type can be rigid and it can be flexible. Now in the case of rigid and flexible, let's explain in terms of open and closed only. Rigid is something basically which cannot change itself. That means again in the case of closed system, okay, that means when something is so fixed, you cannot change that. You cannot change this complete boundary. It will remain as it is. So in closed system, we shall obtain rigid boundary. Now in flexible is again seen in the case of open system. How? If I'll keep a piston over here at the top, let us consider this is my piston. If I'm applying some pressure, it will go down. Okay, if I'm not applying some pressure, if there is internal pressure more, so it will move in the upward direction. That means this basically can change. This is basically piston. So this is a flexible boundary that separates both system and surrounding. It is seen in which case? In the open system. Okay, clear everyone. We have one more type of boundary, that is adiabatic and diathermic, but that we'll be understanding when we'll be moving on to the heat and work part as well. Okay, students. So shall we move on to the next part? I guess now you're clear with the term system, surrounding, and the boundaries. Yes, okay. Now, students, comes the next important and very interesting part, that is state of a system. What is the state of a system? If I'll ask you what is your state, you will say, ma'am, I'm so cool, I'm so chill, I'm so calm. So that defines your state, right? The state which is based upon your mental health, the state that is based upon your physical health, you define your state in that terms. But what about system, students? How do you define a state of a system? So a state of the system basically is the condition in which the system is present. Similarly, the condition in which you are present is your state, right? So let us consider, if I am healthy, if I am happy in my life, so my state is so well and good, right? But if I am sad, I'm not happy, I'm not well, I'm not feeling good, okay, I'm having any health problem, so I'm not well, no, my state is not well, no. So that is what is the state of a person. But state of a system is in which a system is present, the conditions in which it is present, right? So state of thermodynamic system is described by measurable or macroscopic properties. Now you can define state in terms of pressure, volume, temperature, number of moles. You can define them in that terms. That means according to the state variables, right? Now, students, there are types of thermodynamic variables that we are going to understand. One is basically your state function, another one is your path function. So any of the thermodynamic variables can be explained by these two terms over here, that is state function and the path function. State function is something which depends upon the state basically, okay? That means initial and the final position. But what is path function? Path function which depends only upon the path through which this reaction is being proceeded, right? Let's understand about them in detail. So, if I'll talk about state function, students, state function is independent of the path taken. For example, if you are doing a certain reaction, it doesn't depend if you are going through from A to B, or you are moving from A to B, then to A to D, then to B, okay? So, it doesn't depends upon your path, but it will always and always depends upon the initial and the final position, right? It depends only upon the state of the system. Okay, so talking about path function, it is dependent upon the path taken through which path the thermodynamic process is being occurring. That is what is a path function. It depends upon the how the state of the system has been achieved, through which way it is being achieved, right? It depends upon that state. All paths result in same value. Different paths may result in different value. Okay. Example of a state function, very very important. A lot of questions in competitive exams you may observing with what is a state function, what is a path function. They will give you certain options and they will ask you identify the state functions among the following, identify the path functions among the following, right? So you can do accordingly. State functions example are internal energy, which is either represented by U or by capital E, okay? It is one of the same things. Then comes the enthalpy, which is represented by capital H. Then comes your entropy, represented by capital S. Thermodynamic temperature, that means by T. Volume and pressure. So all of these terms depends upon the initial and the final position. But if I talk about path function, heat and work, both heat and work, heat is represented by Q and work is represented by W. They both are what? Path function. Now many a times they will give you certain options and they will give you heat and work also. So you should know that heat and work is a path function which depends upon the path followed but not on the state of the system. Clear everyone? Okay. Let's move on to the next and most important term, that is what is an extensive property and an intensive property. So when you will be solving some of the questions, the general things, if I'll ask from the introductory part of thermodynamics chapter, many questions are asked from state function, path function, extensive property, intensive property, right? Now what are extensive and intensive property? Basically, these are types of thermodynamic properties. Now what is exactly extensive property? A property which is dependent upon mass is an extensive property. An intensive property is that property which is independent of the mass. Okay. So I can say extensive property is a property. It is a property which is dependent upon the mass or the matter, I would say. But what is an intensive property? Property which is independent which is independent of mass. That means that does not depend upon mass. Let me tell you students, extensive properties are additive in nature while intensive properties are non-additive in nature. So these are additive in nature. You can add them. They are additive in nature while intensive are non-additive in nature. They are non-additive in nature. Other than this, students, if I'll talk about extensive properties, no, if you'll divide two extensive properties, you will get an intensive one. Always remember this. If you'll divide two extensive properties, you are going to get an intensive property. Let's talk about some examples with regard to extensive and the intensive ones. So if I'll talk about extensive property, let's talk about mass. This is an example. Mass, volume, because they all are dependent upon the mass of the system or the matter of the system. So mass, volume. Moreover, I can say that let's talk about heat capacity. Right? These are mass dependent terms. Let's talk about intensive one. pH, which does not depends upon mass. Temperature, that does not depends upon mass. Pressure, that does not depends upon mass. Melting point, that does not depends upon mass. Boiling point, that does not depends upon mass. See, heat capacity is an extensive property, but specific heat capacity is an intensive one. So specific heat capacity, okay. Then let's take some more examples. For example, if I have molarity. Now what is molarity, students? Molarity is number of moles of solute by volume of solution. Now let me tell you, number of moles is also an extensive property. So extensive by extensive gives an intensive property. No, that means molarity is an intensive property. Molality is an intensive property. Normality is an intensive property. Now you know what is an extensive and what is an intensive property, students. You can pause the video, write down each and every terms that I'm explaining you over here. Let's move on to the next part, that is types of thermodynamic processes. Now we are understanding there are certain processes in nature that occur thermodynamically. So what are these? Let's understand them in detail. First of all, what do you refer to as a thermodynamic process? What is a thermodynamic process? Let's talk about it. So the method or the process, I would say, by which a system can change the state from one state of thermodynamic equilibrium to the another state. For example, if I can say that, let's consider my initial system was having a pressure of 1 atm with volume of 10 liters and temperature as 273 Kelvin. After few time, the pressure changed into 3 atm, volume changed into 20 liters, and then the temperature also changed. So that means when a system changes its states, that means physical state, that I would say that pressure, volume and temperature variables are being changed into another part, from P initial to P final, V initial to V final, T initial to T final. That means it is changing its variables. So that is what is a process being occurring over there, when a state is being converted into another state. Okay, so let's talk about them in detail. The very first that we are going to start is isothermal process. Now what do you refer to as a term iso? Students, always remember, whenever you will be seeing iso over here, that refers to as same. That refers to as what, ma'am? Same. Now what is same over here? I said isothermal. Thermal means temperature. Thermal means what? Temperature. So when we see same temperature, that means when temperature, students, is constant, that term is isothermal process. That means delta T over here will be what? 0. Now what is delta T? Change in temperature. It will remain as what? 0. I've already explained you it is a state variable. It will depend upon initial and final terms. So final temperature minus initial comes out to be 0 because temperature remains same. This is what is isothermal process, right? Do you remember Boyle's law? We studied in states of matter. What was Boyle's law? P1 V1 is equivalent to P2 V2, right? So this is basically the Boyle's law that is based upon the isothermal process also. Now, if you have to draw a curve between pressure and volume, it is going to be like this, because see, in isothermal process, pressure is inversely proportional to volume. So I have revised your previous chapter states of matter also over here. Let's talk about isochoric process. Now iso again refers to, ma'am, same. Choric here will be used for volume, students. When there is same volume, that means that is isochoric process. So when there is same volume, students, that means delta V, change in volume, is what? Is 0. So if again I have to plot a graph of PV only here and volume my over here is same. So can I obtain this part, right? Right, because my volume over here is constant. Yeah, so this is for isochoric process. Let's see the next process, that is isobaric process. Now iso again here refers to as same, baric refers to as for pressure. So when we see there is a same pressure, that is isobaric process, that means delta P is now 0. That means if I have to plot a graph of pressure and volume, now my pressure is constant but volume is changing, no? So this can be the graph for isobaric process. Let's talk about adiabatic process, where heat change is going to be 0. Delta Q is going to be 0, right? And basically, if I had to draw a graph all together for all of them, so see, this was for isothermal. Adiabatic will have same but less than that. Okay, so this is for adiabatic. Okay, and this was basically for which one? When volume is constant, that means for isochoric. And this one is for isobaric. So such kinds of graph you can observe in the question paper also. Let's move on to the next part. Now comes reversible and the irreversible process. What are reversible and the irreversible process? Reversible process is something which takes a lot of time to complete. Basically, this is a slow step, and reversible is something, if I'll talk about a certain reaction, I would say when reactants convert into product and product also have a tendency to convert back into reactant, is what is a reversible one. That means when we can say there is a forward direction reaction, also there is a backward direction reaction also taking place. But what about irreversible reaction, ma'am? Irreversible reaction is something which when is converted, it cannot be converted back, right? So I would say that what is a reversible one, which is a slow step process, and irreversible one is a fast step process. In reversible thermodynamic processes, what are you going to do? That, for example, here it is occurring in a various steps. It is a slow process, but it will occur in various steps. And each step is going to be in equilibrium with each another, with the previous one, right? But in irreversible, as I've already told you, it occurs in a quick interval of time. So there is no equilibrium that is attained in between. Equilibrium shall be obtained either in the initial part or in the final part. That means at the start or at the end, right? So this is what is a reversible process and an irreversible process. Let's talk about it, students. So a reversible process is a slow process, everyone, right? Each stage is in equilibrium with the previous one. Each stage is at an equilibrium from the previous one. But in the case of a reversible, in this process, system attains final stage from the initial stage with a measurable speed. Here the speed is measurable and it occurs very fast. Moreover, during the transformation, no equilibrium maintained between the system and the surrounding. In between, there is no equilibrium attained. It will be attained either in the start or at the end. Clear, everyone? Now what we are going to do is about internal energy. Always you should remember internal energy is either represented by U or by E. Okay. Now what is an internal energy? See, always remember that we can only calculate change in internal energy. We cannot calculate directly what is an internal energy or any part of it. We can always calculate the change, that means initial and the final thing, right? So internal energy is something which is basically comprised of many energy terms all together, that is transitional, vibrational, rotational, electronic energy, all of them together. It is basically a state function, already told you. It depends upon the initial and the final state of a system. Moreover, it is temperature dependent quality. If I'll say you that it is an isothermal process, always remember internal energy is temperature dependent term. So if temperature is constant, internal energy will become 0. So that means it is temperature dependent quality. Next part. It is an extensive property. Why? Because it depends upon the mass of a system. So it comes under the extensive property. Next, internal energy change during cyclic process is 0. Why is it so? See what happens in cyclic process. For example, if you're starting from this part and you're coming back to this point. So initial and final point is same, no? So, and I already told you it is a state function. State function is something where we have a change in final and the initial points. So when final and initial both are same, it will be 0. So that means internal energy change, that means delta U for a cyclic process is going to be what, ma'am? It is going to be 0. Let's move on to the first law of thermodynamics. Very, very important, very, very easy. What is first law of thermodynamics? First law of thermodynamics is based upon the law of conservation of energy. That energy can neither be created nor be destroyed in any chemical reaction. It is going to be conserved. It is going to remain same, students. Clear, everyone? Now always remember, as it is based upon the conservation of energy, so we'll always be saying that delta E or delta U, that is internal energy change, is equivalent to Q plus delta W. So this is what is the formula which is based upon the first law of thermodynamics. What is delta U over here, students? Delta U over here is change in internal energy. Change in internal energy. What is Q over here? Q is basically heat of the system, right? What is delta W? Work done. Work done, right? Now see students, let me tell you one more thing. There is one more formula that you will be studying in the work done. I am going to explain you now only. That work done is equivalent to minus P external delta V. What is P external? P external is the pressure and delta V is change in volume. So if we'll equate this over here, you will get delta U as Q minus P delta V. So this is one more formula based upon the first law of thermodynamics. So these two formulas are important with regard to first law of thermodynamics. Speaking again, what is first law of thermodynamics? It is based upon the principle of law of conservation of energy, that energy can neither be created nor be destroyed in any chemical reaction. Let's move on to the next part. Now we are going to calculate delta E or delta U for all the processes. Let's start with the very first one over here, students. So we basically have for isothermal process. See, for isothermal, I already told you that delta E or delta U, I would say, is a temperature dependent term. So delta U will become 0 for an isothermal process. Clear everyone? Clear everyone. Okay. Now coming to the next one, for isochoric process. For isochoric, we very well know that isochoric, that means change in volume is 0. If delta V is 0, we know that work done is minus P external delta V. If delta V is 0, work done whole will come out to be what? 0. Now W is 0 and we know that delta E or delta U is what? Q plus W as per the first law of thermodynamics. If W is 0, what will be delta E? Delta E or delta U will be equivalent to Q. Clear? This is for isochoric process. Let's talk about for adiabatic process. See, very well know for adiabatic, Q basically is going to be 0. The heat change is 0, right? So delta E basically is what? Q plus W. And if Q is 0, delta E will be equivalent to the work done, right? This is for what? For adiabatic process. Clear everyone? Let's see the next one. When a gas expands against a constant pressure, so it's very simple thing. We know that W is equivalent to minus P external delta V, right? This is the formula when a gas expands for, when we are talking about against a constant pressure. So the formula you can directly use is delta E or delta U is Q plus W. That means delta U is equivalent to Q minus P external delta V. You can use this formula. Now comes the case of vacuum. See, in vacuum, whenever we are talking about vacuum, pressure external is going to be 0. If pressure external is 0, what will be W? W is minus P external delta V. If minus P external is 0, W comes out to be 0. If W is 0, we very well know delta U is Q plus W. If W is 0, internal energy will be equivalent to what? Q. Very simple, easy. Okay. Let's move on to the next part. Now let's understand about work in detail, though I've already told you what is work basically. Work basically is minus P external delta V, that is the pressure being applied at a particular area. Now you have understood about, what is the pressure, force exerted per unit area, and what is work done? Minus P external delta V, right? Mechanical work. What is mechanical work? When you apply some force and the displacement occurs, that is mechanical work. But thermodynamic work, what that is? Minus P external delta V. More about work done, students, I would say that work basically is a path function. Very important. Many a time students just get confused with state function and path function. Always remember Q and W. That means heat and work are path functions. Coming to, there are some terms that you are going to observe which is quite different from physics and chemistry. That is the sign over here. See, whensoever I will be saying heat given to a system. Now, for example, I am system and someone is giving me heat. So, I'm gaining something, no? Always remember, heat given to a system is always positive. Next part. Heat given by a system. Now, if I'm saying heat given to a system, that means Q will be positive. Q is heat, no? Next part. Heat given by a system. Let us say I am a system. I'm giving some heat. That means I'm losing something. So, you can learn in that way. Q is going to be what? Negative, right? Next comes out to be work done on a system. Let us say I am a system and work is being done on me. So that means again it is a positive value. And work done by a system, that means I am doing a work, so that becomes a negative value. So this is my way to explain you how you can learn it out. Heat given to the system, by the system, work done on the system, by the system. So these are the sign conventions that you need to remember. Clear, students? Now comes the next part, that is work done in various processes. So there are various processes in which we are going to understand about the work done. Let's start with them. So the very first is work done in irreversible isothermal expansion. So in irreversible isothermal expansion, it is very simple, that is minus P external delta V. What is work done? Work done is minus P external delta V. Right, now comes work done in reversible. You know what is reversible reaction? Isothermal, you know, when temperature is constant. Expansion. So for this, students, work done formula is basically going to be minus nRT ln V2 by V1. This is going to be the formula for reversible isothermal expansion. Now, if you have to calculate it, you have to convert this ln E into log to the base 10. So basically that comes out to be minus 2.303 nRT log to the base 10 V2 by V1. This is going to be the formula of work done in reversible isothermal expansion. Let's consider if they'll give you the case of pressure. How are you going to do this? We know for isothermal process, P1 V1 is equivalent to P2 V2. So P1 by P2 is equivalent to V2 by V1. So you can replace it over here because it is for isothermal. Another formula is going to be minus 2.303 nRT log to the base 10 P1 by P2. This is one more formula for work done for reversible isothermal expansion. Everybody please write it down so that I can move on to the next part now. So students, I hope so everyone has written this. Okay, now let's see the next part. Work done during expansion and vacuum. Now only we have seen that, ma'am, in vacuum, P external comes out to be what? P external comes out to be 0. Yes, everyone? So now if P external is 0, what is work done? Work done is minus P external delta V. If P external is 0, so work done will also be 0. For which case? During expansion and vacuum. Clear? Now comes the next part, work done in adiabatic reversible expansion. See, in work done in adiabatic reversible expansion is what? Work done is equivalent to minus NR. This is T2 minus T1 by gamma minus 1. Sorry, here negative sign won't come. Yeah. So basically this is the formula. What is gamma, students? Gamma basically is Cp by Cv. I will be coming to this part also. What is Cp? What is Cv? Okay. But first of all, write it down. This is the formula for the following part. Clear? NR T2 minus T1 by gamma minus 1. Now comes work done in adiabatic irreversible expansion. So it is very simple, students. It is equivalent to minus P external RT final by P final minus RT initial by P initial. Clear, everyone? This is for irreversible expansion. So yes, students, let's understand about enthalpy now. What is enthalpy? Enthalpy represented by H. What is enthalpy? Represented by H. Students, you can never calculate H directly. You can only calculate change in enthalpy, that is delta H. Now, what exactly is enthalpy? Enthalpy basically is heat change at constant pressure and constant temperature. This is what is enthalpy. How are you going to calculate? Very simple formula. Change in enthalpy is equivalent to internal energy change plus delta Ng RT. So this is one formula through which you can calculate the enthalpy very easily. Now what is delta Ng over here? Delta Ng is number of moles of product minus the number of moles of reactant. And G here stands for gaseous reaction. Let us consider I have A gaseous, 2A gaseous plus 3B solid being converted into 3C solid plus 4D gaseous. So what is change in number of moles? That is going to for only gaseous. This is solid, you won't include it. This is solid, you won't include it. That is final minus initial. Final is 4 written over here, minus 2 is written for gaseous. So delta Ng is 2. Always remember you are going to use it for gaseous ones. Let's talk about the next part, that is heat capacity. Now what is heat capacity? Basically that is change in heat when 1 degree temperature, when there is a rise in 1 degree Celsius temperature. Okay, so basically that is equivalent to Q by delta T. Heat capacity is represented by C and it is equivalent to heat by change in temperature. Always remember there are two types of heat capacities, that is molar heat capacity and specific heat capacity. Molar heat capacity basically depends upon when I would say that 1 mole of a substance is being heated in order to raise the temperature by 1 degree Celsius, and when I'm saying that 1 gram equivalent is used, that is basically your specific heat one, right? So in the case of molar one, we are going to use the terms as moles over here. That means it is going to be Q by N delta T, and for the specific one I would say that it is equivalent to Q by M delta T, because it is dependent upon the mass 1 gram, and it is dependent upon the moles, it is 1 moles. It is when 1 gram amount of gas, when we are talking about to change the temperature by rise in temperature by 1 degree Celsius, and when we are talking in terms of moles, that is going to be the molar one. Okay, now students, here comes your Cp by Cv. Always remember that Cp by Cv is what is your gamma. Cp by Cv is what is your gamma. Always remember Cp minus Cv is also equivalent to the gas constant, that is R. Now coming to for different gases, see if you have monoatomic gas, Cv value is 3R by 2, Cp value is 5R by 2. For diatomic gas or linear polyatomic gas, you are going to get 5R by 2 as Cv and Cp is 7R by 2. What is for non-linear polyatomic gas? Cv is 3R, Cp is 4R. So what is Cp by Cv is gamma. You can calculate gamma and you can use that for the work done in adiabatic process. You can use this gamma value over there and calculate work done. Clear? Now students, come about enthalpy change. There are various enthalpy change that we should always know. The very first is standard enthalpy of a reaction. Standard enthalpy of a reaction is represented as delta H naught. Now what is the standard state? When we'll say that temperature and pressure are kept at a standard point, when I'll say that, you know, pressure is 1 atm and temperature is your 27 degrees, temperature is 273 Kelvin, like that. So I can say that enthalpy change for a reaction when all the participating substance are in their standard state. Okay, that is what is delta H naught. Now comes enthalpy of formation. What is formation? Something to being formed. So when I'll be saying that when 1 mole of a substance is directly obtained from its constituent elements, when 1 mole of a substance, at that spot of time, the enthalpy is basically enthalpy of formation, which is represented as delta HF for formation. Next comes enthalpy of combustion. Combustion means when you are reacting in the presence of oxygen, in the presence of air, that is with O2. So when 1 mole of a substance undergo complete combustion, that is enthalpy of combustion. Clear? Next basically is enthalpy of hydration. What is that? When one mole of an anhydrous compound combines with the required number of moles of water to form a specific hydrate, that is enthalpy of hydration. Next is enthalpy of neutralization. When 1 gram equivalent of an acid is neutralized by 1 gram equivalent of a base, that is enthalpy of neutralization. Next part, enthalpy of ionization. The name itself says ions. So amount of energy required to completely ionize 1 mole of a weak electrolyte, that is enthalpy of ionization. So you should know all of these types of enthalpies, right? Next comes your Hess law, students. Hess law is something, if I'll say that a reaction can occur in a single step, or that same reaction can occur in various steps. Both of them, the enthalpies is going to be same. Either if that is occurring in a single step or in a multiple step, the energy change is equivalent to be same. They should be same, right? So it states that total heat change during the complete course of a reaction is same whether the reaction is made in one step or in several steps. It is going to be same. For example, if I'll say that A is being converted into B, delta H for this one, let us say this is first one, right? X. And if I'll say A converts into C first, C converts into D, and then D converts into B. So when you're going to add them all together, what you are going to get? You'll get A plus C plus D gives B plus C plus D. That means A is changing into B. So that is same way. If it is occurring in same steps or in different steps, the enthalpy change for this main reaction comes out to be same as that was for the single step. Clear? Now students, comes the next part, that is second law of thermodynamics. What is second law of thermodynamics? It states entropy of universe always increases in the course of every spontaneous change. Now what is entropy? It states that it keeps on increasing. It's a positive value. But what is entropy? Entropy, students, is the randomness of the molecules. Randomness of the molecules, right? What is entropy? Entropy basically is represented by S, and we can always calculate delta S. We cannot calculate entropy directly. So it is Q reversible by time taken. That is what is entropy. Moreover, students, there are some formulas. Again, I'm speaking, I'm not telling the derivation part because this is a quick recap session. So you can quickly revise and use them in the questions. So the very first is for isothermal reversible one. delta S for the system is minus nr ln v2 by v1. Always remember, delta S for system plus surrounding is all equivalent to the delta S for the universe, and it always says that it always increases for the universe, right? Next part, for irreversible isothermal, expansion, delta S surrounding will be minus p external v2 minus v1 by t, and it is always less than the reversible one. Okay, it will always be less than the reversible one. Now students, next come the part that is what is a spontaneous reaction. Spontaneous reaction is something which occurs on its own, right? And for spontaneous reaction, always remember delta G is going to be negative. Clear? Next, a process that has an urge or a natural tendency to occur either on its own or after proper initiation under a given set of condition is what is a spontaneous reaction. Why I told you spontaneous reaction? Because we have to understand a term that is Gibbs free energy. Gibbs free energy is basically G, and we can always calculate delta G, that is change in Gibbs free energy. What is that? Delta G is equivalent to delta H minus T delta S. So this is one formula again for the Gibbs free energy, and always remember, for a spontaneous reaction delta G will always be negative. For a spontaneous reaction delta G comes out to be what? A negative term. Clear everyone? Moreover students, for a reaction in progress, what is delta G? Delta G is equivalent to standard Gibbs free energy plus RT ln Q. What is Q? Reaction quotient. So basically delta G is equivalent to delta G naught plus RT ln Q. Now this questions is generally asked in so many questions, that at equilibrium what happens? At equilibrium the Gibbs free energy change is equivalent to 0 and reaction quotient will be equivalent to the equilibrium constant. So a new formula you can calculate for standard Gibbs free energy, that is minus RT ln K, because delta G is 0, so when you're going to put all the terms it will be minus RT ln K. Clear? Okay students, now comes the last part, that is third law of thermodynamics. What does it states? That the entropy of a perfect crystals of all pure elements and compounds is 0 at absolute 0 temperature. This is what is explained by third law of thermodynamics. And they have also given a certain formula that the delta S for the surrounding is equivalent to minus Q for system by T. That means minus delta HT, delta H. That means again, that is enthalpy change by the temperature, right, at a particular temperature. So that was what was the third law of thermodynamics. So students, here we are going to end our today's class of thermodynamics, and we have completed each and every topic. Again repeating, we have not derived the derivation part, the formula parts. I just directly told you for which particular process you have to use which formula, right? So what's your work now? Your work is to solve as many as questions as possible for this particular chapter, and we shall be now meeting in the next lecture. So till then, keep smiling, keep learning. Thank you so much and have a good day, my dear students. Thank you so much.